Hello everyone, this is my second lecture in Open Channels, and we'll discuss here alternate stages of flow, critical depth, hydraulic jump, non-uniform flow, and flow around channel bends, which are the last part of the last topics in Open Channel flow. There are two stages or depths of flow that correspond to the same energy content and same discharge. We call them alternate stages of flow, and each is called the conjugate depth of the other, and vice versa. The lower stage, where Froude number is greater than 1 and therefore characterized as rapid shooting flow, so the depth in the lower stage is less than the critical depth. So that's the information necessary for you to understand more about open channels. The upper stage, where the Froude number is less than 1 and therefore characterized as subcritical flow and tranquil flow, where the depth is greater than the critical depth. So depth in the upper stage is greater than the critical depth. The critical depth is the depth corresponding to minimum energy content, and therefore the Froude number is equal to 1 and is characterized by a wavy surface. So take note of the characteristics when the depth of flow in the channel is critical. It is characterized by a wavy surface, and the Froude number, which will be defined later as the ratio of inertia to gravity forces, is equal to 1. The critical depth formula applicable to any shape is given by, which we will derive also later, capital Q square over G equals area critical cube over top width. So that's the general formula, but we will derive this as we move on. Area sub C is the cross-sectional area at critical depth, and B is the top width of the water surface. When the channel is rectangular, so take note this is only for rectangular channel, the critical depth formula, although there's no critical depth here, it is in the area critical where critical depth will appear, is cube root of quantity small q square over G. That's the critical depth formula for rectangular channel only, or for very wide channel. So when the problem states wide channel or very wide channel, then we can treat the very wide channel as rectangular one. So that's the critical depth formula. Small q will only appear for rectangular channels. Capital Q for all sections. Even for rectangular section, this is applicable. And we will also derive this later. So where small q is thought of as the discharge per unit width of the channel. So 1 meter width, the discharge through that 1 meter width is that small q. So therefore it is equal to big Q divided by top width, or big U over small b, because for rectangular channel it is small b. This is the specific energy. So therefore, since critical depth occurs where content of energy is minimum, then it is also equal to critical velocity head plus critical depth. That's the minimum energy when the depth of flow is critical. Critical velocity head plus critical depth. Since later this critical velocity is square root of G times hydraulic depth critical, so critical velocity square therefore is G hydraulic depth critical. We can cancel G, so it is also hydraulic depth critical over 2 plus critical depth. And that is also for all sections. Now for rectangular sections, this critical depth becomes critical depth plus 1/2 of critical depth plus critical depth, because the hydraulic critical depth for rectangular section is simply the critical depth. So it is 3/2 of critical depth for rectangular sections only, but this formulas for all sections. That's for all sections. So to illustrate, we have here an side picture of the channel. This is the critical depth, and we have the depth, alternate depth in the lower stage and in the upper stage, where they have the same discharge and energy content. So this is the depth in the lower stage. This is the alternate depth in the upper stage. So alternate depth in the upper stage, the upper. Then if we plot the depth versus Q, then this is the curve. Take note, at critical depth, the discharge is maximum, but the critical depth is between the lower and the upper stage, the alternate stages of flow where the discharges are the same and the discharges are the same. So Q in the lower stage is equal to Q in the upper stage, because in the lower stage, the cross-sectional area is smaller, but the mean velocity of flow is higher. In the upper stage, the cross-sectional area is bigger, but the mean velocity is low. That's why there's a big possibility, or that's why Q in the lower stage is equal to Q in the upper stage. That one. Then at the critical depth, the discharge is maximum, Q max. Then if we plot depth versus energy, the curve will be asymptotic to E equals D, because as the depth increases, the velocity head decreases and it becomes negligible, but it will not touch, of course, the line E equals D. So that's the curve, and at this level here, we have minimum energy content that corresponds to the critical depth. And for the alternate stages of flow, depth in the lower and in the upper, they have the same energy content. So that's why they are vertically aligned. But at the critical depth, the content of energy is minimum. That's it. In the lower stage, the Froude number is greater than 1. It is characterized by supercritical flow, rapid shooting flow. In the upper stage, the Froude number is less than 1, tranquil flow, subcritical flow. That's it. But for critical depth, it is characterized by a wavy surface. Froude number is exactly equal to 1. So that's it. Lower stage, Froude number is greater than 1 because the velocity is higher. At the upper stage, Froude number is less than 1 because the velocity is lower. Oh, that's it. So moving on. So if this is the side of the channel, the depth of flow is critical. And let's have the cross-section of the channel. We consider a strip on top where the top width is B and the differential depth is DD. So that's the differential area, B times D sub D. The cross-sectional area is denoted by A. So this blue strip here, this blue strip is differential area, which is equal to top width times differential depth. Because at that level, the velocity is the same at all points on the surface. So specific energy is velocity head plus depth. So replacing velocity in general by Q over area, quantity square over 2G plus depth, then specific energy is Q square over 2G times area to the negative 2 plus depth. So take note that the area is a function of the depth, so that is also a variable. The variables here are area and the depth. So minimizing specific energy, because the definition of critical depth is the depth corresponding to minimum content of energy. So derivative of E with respect to the depth is q squared over 2g times negative 2 area to the negative 3 times the derivative of area with respect to depth plus derivative of depth with respect to depth is 1. Then equate to 0 because we're going to minimize it. So simplifying, we have 0 equals q squared over g negative area to the negative 3. Since differential area is BDD, differential area, so differential area DD over DD is top width. So that's why this is equal to the top width B plus 1 equals 0. Transposing this to the left, we have q square over g area cube, q square capital B over g area cube equals 1. Then rearranging to form the critical depth formula, q square over g equals area cube over B. This was the formula earlier introduced, where area is the area at critical depth and B is the top width at critical depth. So this is applicable to all shapes. So where is the critical depth in this formula? It's in the area. The critical depth is a function of that critical area there. So it all depends on the shape of the area. So since Q is area times critical velocity, because this is the critical depth formula, so replacing capital Q by area critical velocity, then cancelling out area square, then we have V sub C square equals G area over B. V sub C square over G equals area over B. Remember that area over B is hydraulic depth, but because this corresponds to critical depth or area at critical depth, the ratio of critical area to top width is critical hydraulic depth. So V sub C therefore is square root of G times area over top width, which is the critical hydraulic depth. So therefore, the critical velocity in general for all sections is square root of G critical hydraulic depth. So that is applicable for all sections. For rectangular channels, the hydraulic critical depth is simply the critical depth. So the critical velocity for rectangular sections is simply square root of G times critical depth. So for rectangular shapes, area is bottom base width times critical depth. And capital top width is also the bottom base for rectangular sections. So remember, capital Q is the product of the unit discharge per meter width of channel times the width of the channel. So it is small q times V square over G. Then critical area for rectangular shapes is B times critical depth, quantity cube over B from this formula here. Capital B is just small b. So q square B square over G equals B cube D sub C cube over B. B square and B cube over B is the same, so we can cancel B square. That's why we are able to derive critical depth for rectangular sections, cube root of small q square over G. That was the formula earlier introduced. So this is the critical depth formula for rectangular channels only. And the critical velocity is square root of G critical depth for rectangular shapes or rectangular channels. We define Froude number as the ratio of inertia to gravity forces. So V sub C over square root of G hydraulic depth critical equals 1 from this formula here, V sub C divided by this square root of G hydraulic depth critical. And this is actually the Froude number, velocity over square root of G hydraulic depth or depth for rectangular sections. That's the Froude number at critical stage. So that's why the Froude number when the depth of flow is critical is equal to 1. So in general, Froude number is mean velocity of flow divided by square root of G hydraulic depth. In general, not necessarily at critical, because if it is critical, then this is V sub C, then hydraulic depth critical, and it is equal to 1. So that's the general formula for all sections. For rectangular sections, you just replace hydraulic depth by depth. So Froude number for rectangular section is simply velocity, mean velocity of flow over square root of GD. So specific energy is velocity head plus depth. E minimum therefore is critical velocity head plus critical depth as introduced earlier, and it is now clear here. So E minimum equals, since V sub C square is G hydraulic depth critical over 2G plus critical depth, then we can cancel G. So that's why E minimum is 1/2 of hydraulic depth critical plus critical depth. That is for all sections, and this is for rectangular sections because the hydraulic depth critical is simply critical depth for rectangular sections. So 1/2 of critical depth plus critical depth is 3/2 of critical depth. That is for rectangular sections only. This is for all sections. So that's for all sections. Hydraulic jump is a phenomenon where the water surface or water stage rises abruptly due to the retarding water flowing at the lower stage. This happens when normally after water rushing down from the spillway of the dam encounters an abrupt change in slope from being very steep to flat. So as a result, a hydraulic jump occurs. You also observe this, but you're unaware that it is a hydraulic jump phenomenon, especially during heavy downpour on a street where we have a very steep slope. Then the slope changes abruptly to almost flat. Then a hydraulic jump phenomenon will occur. So hydraulic jump is important because it is used as an energy dissipator. There's a need that a hydraulic jump occurs because rushing water is very devastating, especially its effect downstream of the channel. So a hydraulic jump must occur so that its devastating effect will be lessened or reduced. Then the power dissipated would be equal to weight flow rate or Q gamma times the head loss in the jump. So hydraulic jump will only occur if its flow is from supercritical to subcritical. But I want to emphasize that these stages or depths in the jump are not equal to the alternate stages or alternate depths as before. It is because there is head loss in the jump. So the depth after the jump is lower than the alternate stage in our preceding topic. So again, depths before and after the jump are not alternate stages. So this is the situation. We have a spillway of dam, for example, water rushing down, and the velocity or the flow is obviously super critical. Then because it encounters this abrupt change in slope from very being steep to almost flat. This is almost flat. This is the apron of the dam. So the mass of water loses momentum. So as a result, we have this hydraulic jump phenomenon. So call that section 1 before the jump. Then this is section 2 after the jump. The depth is depth sub 2. And this is the energy grade line. So we have depth at section 1, velocity head at section 1, then depth at section 2, velocity head at section 2, then we have the head loss in the jump. So all you have to do is equate this vertical distance to that vertical distance. So the velocity, mean velocity of flow at section 1 is V1, at section 2 V sub 2. So velocity head plus depth or specific energy at section 1 equals velocity head plus depth at section 2 plus the head loss in the jump. Therefore, the formula for the head loss in the jump is simply specific energy at section 1 minus specific energy at section 2. So because the hydraulic jump occurs in a short distance, any change in elevation in the bed is negligible. So this is assumed to be flat. Unless otherwise, it is emphasized in the problem. So this is the acceleration. V1 is greater than V2, so it means acceleration is negative. Then we apply Newton's second law, summation forces equals mass times acceleration, in this case, the basic one. So F1, this is the hydrostatic force at section 1. Then we have F2, hydrostatic force at section 2. So V sub 2, final velocity, equals initial velocity plus acceleration, which is negative, times time. So acceleration therefore is V1 minus V2 all over time. So applying Newton's second law, summation forces equals mass times acceleration. If you can recall from dynamics, where the positive forces are those forces in the direction of acceleration, opposite to acceleration will be treated negative. So therefore F2 minus F1 equals mass times acceleration. F2 is hydrostatic and F1 is also hydrostatic. Mass is density times volume. So gamma barred H2 area 2 minus specific weight of water barred H1 area 1, or any liquid in general, equals density times volume, which is mass, times acceleration, which is V1 minus V2 over time. So factoring out specific weight, then we have barred H2 minus barred H2 area 2 minus barred H1 area 1 equals Q, volume over time is Q, then density quantity V1 minus V2. So in general, hydrostatic force at section 2 after the jump minus hydrostatic force at a section before the jump equals Q rho quantity V1 minus V2. So I use this formula to easily remember it than this form because it's longer. So remember that these are hydrostatic forces after minus before equals mass flow rate times quantity V1 minus V2. Of course, V1 is greater than V2 to make this positive. So that's the general formula for hydraulic jump, and this is applicable for all sections. Now, if the section is rectangular, then this is the formula that we're going to derive. Small q square over g, or unit discharge per unit width of channel, applicable for rectangular sections and for very wide channel, equals depth 1, depth 2 over 2 quantity depth 1 plus depth 2. But that is only applicable for rectangular sections. So F2 minus F1, the difference in hydrostatic forces between sections in the upper and lower stages of the jump. But I want to emphasize that these are not alternate stages because of the head loss. So because of the head loss in the jump, that's why these depths are not alternate depths or alternate or conjugate depths. So let's now derive this equation. So specific weight barred H2 area 2 minus barred H1 area 1 equals Q rho V1 minus V2, where specific weight is density times G. Then barred H2 is simply depth 2 over 2 because the section is rectangular. Barred H1 is depth 1 over 2. And area 2, by the way, is base of the rectangular channel times depth 2. Area 1 is base of the rectangular section times depth 1 equals capital Q is small q times V times density. Then V1 is small q over depth 1. V2 is small q over depth 2. So cancel out density. So let's factor out B over 2, GB over 2, cancel out density only. Quantity depth 2 square minus depth 1 square equals Q square times B, quantity depth 2 minus depth 1 all over depth 2 depth 1 by algebra from here. So we cancel out B. Let's factor this into G over 2, depth 2 minus depth 1 times quantity depth 2 plus depth 1 equals Q square quantity depth 2 minus depth 1 over depth 2 depth 1. Then we cancel out depth 2 minus depth 1, that common factor in the left and the right side. And we have G over 2 quantity depth 2 plus depth 1 equals Q square over depth 2 depth 1. Then finally, we can form this equation just like this. So Q square over G equals depth 1 depth 2 over 2 times depth 1 plus depth 2. So rearranging Q square over G equals depth 1 depth 2 over 2 quantity depth 1 plus depth 2. So that's the formula. That's the hydraulic jump formula for rectangular sections. So non-uniform flow is always expected in the real world. Though uniform flow is expected for artificial channels, there is a certain reach in which non-uniform flow really is expected. So there is a need to consider segments of natural streams where most often the flow is non-uniform, so that uniform flow formulas that we used most of the time, especially in part 1, can be used to approximate such conditions. Therefore, the solutions lead to trial and error and approximate ones, and oftentimes resort to empirical methods. So that we can consider approximate portions of the natural streams to be flowing at almost uniform flow. So almost uniform flow. There's a need to chop it into small segments of the reach so that we can approximate using the formulas for uniform flow. So delta x is just a short distance of a given segment of the stream where we can use approximate methods. So the length of the stream along the sloping bed is denoted by L. So delta x is the horizontal distance between these two sections where we have gradually varied flow, so only applicable for gradual variation in flow, not for abrupt change or very varied flow. So just maybe for this short distance, the depth is not so changing, so the flow is gradually varied. So these are the information. Slope of bed slope is SO. The hydraulic grade line, the slope is denoted by S sub W, water surface slope. And the slope of the energy grade line is denoted by S. All these have different slopes, though near to each other. So we have this distance, therefore, SOX, slope of the bed times horizontal distance delta x. This is the depth at section 1. This is the velocity head at section 1. There is alpha, which is close to 1, but a factor, but that is just approximated as full velocity head. Depth at section 2, velocity head at section 2, then this, because this is the slope of the energy grade line, then this drop in energy grade line is the slope times delta x. So equating these three terms, SO delta x plus depth 1 plus velocity head at 1 equals depth 2 velocity head at 2 plus S delta x. Deriving S delta x as specific energy at 1 minus specific energy at 2. Then we have delta x equals specific energy at 1 minus specific energy at 2 divided by S minus SO. Then if delta x is negative, it means that the flow direction is opposite. If it is negative, if positive, then the flow direction is upstream section would be section 1, downstream section would be section 2. If the result is negative, meaning the upstream section is section 2 and the downstream section is section 1. That's the meaning of that. Then do not consider sections 1 and section 2 as very far from each other. As much as possible, the change in depth should be little so that you can estimate delta x closely, because this formula is just approximate. So what is the slope of the energy grade line? We use the formula for steady or uniform flow from V equals 1 over n hydraulic radius to the 2/3 s to the 1/2. So S is n square velocity square over hydraulic radius to the 4/3, or simply S is nv over hydraulic radius to the 2/3 quantity square. That's for uniform flow. This is non-uniform, gradually varied, or non-uniform. Therefore, we use this for average case. So nvm over hydraulic radius mean to the 2/3 quantity square, where V sub m is the average velocity between sections 1 and section 2. So V1 plus V2 over 2. Hydraulic radius mean is average of hydraulic radii at section 1 and section 2. Hydraulic radius at 1 plus hydraulic radius at 2 divided by 2. That's the meaning of that. Then from there, you can solve delta x. Then you have to consider another two depths again. It may be D2 and D3, so have another delta x then until it ends. And you can compute the total length from sections 1 to the last section. That's it for non-uniform flow. So the last topic will be flow around channel bends. So when the channel is a curved one, then expect that the depths in the inner and outer banks will be different as shown in the general case. So this is the general section. So in the inner bank, the shallower depth, and in the outer bank, we have the deeper depth, which we will denote DO, and the distance, horizontal distance, is denoted by top with capital B. And we have this change in depths in the outer, between the outer and the inner banks, delta D. So we'll develop an expression for that delta D. So this change is due to the hydrostatic forces at the outer and the inner banks. Because this is a curve, there is normal acceleration. This velocity square over r, the expression for one expression for normal acceleration. So this is for the rectangular sections where the width is b horizontal, do, di, and we have here the hydrostatic forces on the outer end of the bank, outer bank, and the inner end of the bank. And that should be equated to mass times normal acceleration. So this is the top view and the center of curvature, radius of curvature. So we have the normal acceleration, which is equal to v square over r. And we consider 1 meter width for rectangular section, so that the volume of this mass of water is simply area of the trapezoid times 1 meter. So summation forces normal equals mass times normal acceleration. F outer minus outer bank minus F inner equals mass times normal acceleration, which is v squared over r, where F outer for rectangular section is gamma of water barred H outer, or dO over 2, because the section is rectangular, times area, which is 1 meter width times depth O. Then hydrostatic force on the inner bank is gamma of water barred H inner, which is rectangular, so half of the depth inner, then area 1 meter by di. Equals mass is density times volume, and volume is area of trapezoid 1/2 of d quantity do plus di times capital B times perpendicular to the board, which is 1 meter, then normal acceleration v squared over r. So factor out gamma of water, which is rho times g, and 1/2, then we have do square minus di square equals density over 2 dO plus di times B times V square over R. So cancel density over 2 and let's factor this out. So G dO minus d inner, quantity dO plus d inner equals B dO plus d inner times V square over R. So we can cancel dO plus di and take note that dO minus di is delta D. The outer minus the inner is delta D. So G delta D equals B V square over R. Finally, delta D or dO minus d inner is equal to V square capital B over GR. So that's the formula in computing for delta D, applicable for rectangular channels only. So that's it for the entire open channel.